So let's say we have this function. X comma y equal to x squared plus y squared minus 9. And we want to find the domain and range as before. And also, we want to talk about whether the domain specifically is the domain open or closed, and bounded or unbounded. And then the range, we will not use those phrases or terminology to talk about the range. And then we'll maybe talk about the graph. So first of all, the domain. Well, looking at this function, I don't see any of my three usual problem functions, right? I don't see a square root, I don't see a logarithm, I don't see division by 0. So if I don't see any of those three exceptions, I'm pretty confident the domain is everything. So here, the domain is going to be all points in the XY plane. There are lots of ways of writing this. You could write it as that, or you could write it as the set containing x comma y such that x and y are both real. Or instead of the fancy R that you use for all real numbers, you could also write it as R2. We really do say R2, you don't say R squared usually. Like you can't say R squared, it's not like super long, but R2 is like the more usual way of saying that. And you can throw in the D2 for some Star Wars action or not. Okay, so this set, the entire XY plane, is it bounded or unbounded? Well, we haven't talked about this much. And I don't know if some classes don't cover this much as others, but when you talk about bounded or unbounded, basically it's bounded if X and Y are both kind of limited in their values. It's unbounded if they're not. So since X and Y can be anything, this set is definitely unbounded. So our domain here, in addition to being all of the real plane, our domain is unbounded. Okay, and probably should start with a different example before we get to this, but is the domain open or closed? Well, when it's the entire plane, the answer is both. Thanks. So we should talk maybe a minute more about what does it mean to be open or closed? There's kind of some very, very specific mathematical definitions about what openness and closedness means. I don't want you to really worry too much about that. So very, very generally, when you think about being open, the kind of set you want to think about is a set like this. The interval from 1 to 4, not including the endpoints. That's an open set. A closed set would be something like the interval from 1 to 4, including the endpoints. So the idea with an open set is that you basically don't include your boundary. And the idea with a closed set is that you do include your boundary. So the entire real plane is both of those. Because, well, one, it doesn't include its boundary. Two, it does include its boundary because there isn't a boundary to include. We can get more specific if we want, but I don't think we need to. So really, as I say this, I'm about to get more specific. So the idea with an open set really is that for any point in your set, you can always find points around it that are still in the set. So like if you think about the interval from 1 to 4, pick any number in there. Okay, 3.9999999. I can still find a number on either side of 3.999 that's in the set still. Whereas that isn't true for a closed set. If I pick the number 4, which is the boundary of the set, I can't find numbers on either side of it that are still in the set. So open sets, you can always find little balls, we call them, around the number that are still in the set, whereas closed sets include their boundaries. So that's kind of the difference. And then the entire plane is both, which is kind of weird. I don't want to get too into it because I don't. Is this something you guys have talked about in class? Open versus closed. You have a little bit. Okay, we can talk more. Like if you like, I'm happy to talk a lot about it if you want me to. But you guys are kind of like do whatever. Let me know if you have more questions. We'll look at another example that's a little less strange. For the range here, well, again, the range is usually kind of a take a look at it and see what you got kind of situation. If I have f of x, y equal to x squared plus y squared minus 9, I'm always looking for an x squared plus y squared and thinking, oh, x squared plus y squared has to be greater than or equal to 0. Always. The smallest it can ever be is 0. So then if it's equal to 0, the smallest this function is going to be is -9. So it looks like the lower end of my range is -9. That's the smallest value we can get. On the other hand, how big does this get? Well, I think I can make it as big as I want, right? Pick x to be really anything you want, and your output's going to be x squared plus whatever y squared is minus 9, right? You can get larger and larger values. There isn't any limit. I suppose since people have asked in the chat about range, or I mean about open and closes as well, let's talk about this set here. So is this open or closed? Or neither, right? So I should point out, neither is also an option. So for the range here, actually, before we talk about open and closed, let's talk about bounded or unbounded. So is this bounded? It's not, right? There is no limitation necessarily on your output values. It's unbounded. You can kind of go as much in one direction as you want. So this is definitely welcome. Thank you. Unbounded. And open, closed, or neither. Well, it's definitely not open. And the way I can see it's not open is because I'm including this boundary point here, right? If I include -9, I can't draw a little interval around -9 that is still contained in my interval. And when I'm thinking about this, I'm really thinking about actually drawing the number line here. So if I draw, say, from -9 to infinity, to be open, any point you pick, you have to be able to make a little interval around it that's still in your interval. That's not true in this particular example. If I pick -9, and I'm saying, I know I'm repeating myself, but I feel like this is something that takes a little while to grasp. So if I pick -9, I don't get a little interval around -9 on either side that's still contained in the set. So it definitely can't be open. Is it closed? I feel like closed is always the harder one for me. Like open seemed to make sense. Like you pick a point, is there something around that point that's still in there? Great, open. But to be closed, basically you have to contain all your boundary points. That's one way of thinking of it. Or another way of thinking about it, which maybe is easier, is if a set's closed, its complement has to be open. Welcome, come on in. So what's the complement of the set? Well, the complement, everything that's not in that set, is everything from -infinity to -9 exclusive. Oh, that's open, right? Anything in there, if I pick a point in there, there's a little interval around it that's also contained in there. So since the complement is open, the original set has to be closed. I'm gonna write this down in a minute. So if you feel like I'm like saying a lot of things and not writing it, you're right. I'm gonna write them down momentarily. So this one is unbounded and closed. So let's talk about that just a tiny little bit. So when you say a set is open, so open, there's a few ways of thinking about an open set. One way, kind of very broadly, is an open set doesn't include the boundary. Another example, or another way of thinking about it would be that for any point in the set, an interval around that point, or really I should be more two-dimensional. A ball around that point is completely contained in the set. And then the third way of thinking about an open set is the complement is closed. And then for a closed set, it's going to be kind of the opposite things. To be a closed set, you can think of it as the set includes the boundary. Yeah, there's the more specific way of describing it is basically, yeah, so this part is going to be a little, basically, for any sequence of points in the set, the limit of that sequence is also in the set. I'll give you an example of this in just 1 second. And lastly, the complement of the set is open. So a lot of times people think of closedness in terms of the complement because it's easier for people to get a grasp of what openness means. So if you're really not sure about closed, be like, well, what's the complement? Is the complement open? Great, then the original thing is closed. So here are some examples of, again, let's go back to our really easy example. This set here, the set from 1 to 4 is open. And a couple ways to see this. Definitely doesn't include its boundary, right? The boundary would be the points 1 and the points 4. If you're looking at this on an interval, there's 1, there's 4. We don't have those points. We have everything in between. So for any point I pick in there, oh yeah, I can pick a little circle or ball around it, and that's included in there. Or you can also say the complement, which is everything that that set is not. So everything from -infinity to 1 inclusive union 4 to infinity inclusive of 4. This set is closed. Includes all its boundary points. Let's look at the other version of this. Let's look at the set 1, 4, which is closed. It definitely does include all its boundary points. And then the other thing you can say, so here's the thing I was saying about any sequence contained in the set is its limit is also in the set. So for example, here's a sequence of points that are definitely included in the set. The sequence a sub n equal to 4 minus 1 over n. For every value of n, this value is in my interval. Let's check. A sub 1 is 4 minus 1, which is 3. That's definitely in there. A sub 2 is 4 minus 1/2, which is 3.5. Definitely in there. And you can see where this is going, I think. If I keep going on, a sub 100 is 4 minus 1 over 100, which is definitely less than 4, so it's still in there. And the limit of this, the limit as n goes to infinity of a sub n is equal to 4. And that is also in there, but notably wouldn't be in this set. So, right, a set that's open, you don't have the limit of each sequence that's in it, contained in it. So these are some of the primary differences between open and closed. And then just for fun, here's a set that's neither. That set is neither open nor closed. It doesn't contain all its boundary points, but you also can't get an open interval around any point that's in it, still in it. So this is neither. But yeah, and then I just want to point out the complement here is open. So the complement, which is the set from -infinity to 1, union 4 to infinity, open like that. This is definitely open. Someone wrote something here. So all problems, Dr. tabs asked to specify if it's open, not open, closed, or not closed, bounded, not bounded. So we cannot just say it is open. So that's fair, but so I should say, once you've said it's open, you've said that is specific enough. Meaning, if it is, well, I should, okay, that's fair. Okay, yeah, technically you could have to specify that something is open and not closed. Most sets, if they're open, they're not closed. If they're closed, they're not open. There are kind of two exceptions. So just to kind of go there, since we've already gone there, here are the exceptions. So this set, so basically whatever space you're working in, the set of everything is both. So if we are working in the real numbers, right, the real number line, then this set, the set containing everything, is both. It's open and closed. And so is the set containing nothing. The set is also open and closed. It's kind of annoying, but it is true. I think it's easier to see that this first one's open and closed because, well, it's definitely open, right? Any point in there, you can pick an interval around it, still in there. And it vacuously contains its boundary points. There are no boundary points. So of course it contains every boundary point because there aren't any to contain. Or you could argue that since this is open, it's, well, I should say not or. And then knowing those two things, you could argue that the empty set's closed and open because the empty set is the complement of everything. So if this is open, this has to be closed, and this is closed, this has to be open. Or you could say the same sort of thing. It's open because every point in it, there's an interval around it that's also contained in it. And that's true because there's no points in it. So for every point in it, great, there aren't any. You can find a circle around it that's still in it. Sure, there's nothing in it. I can do it. It always feels kind of wrong to say that. And then it's definitely closed because it contains all its boundaries. Well, again, there's nothing in there. So of course it contains all its boundaries. So specifically, those are almost, those are the only ones you should have to like kind of think about. If it's like to say it's closed and it's open, any other kind of normal set, if it's closed, it's not open. If it's open, it's not closed. And then this is extendable to more dimensions, meaning if instead you're working in R2, which is where we're usually working for domains of multivariable functions, then the set of all points, so the entire plane, just like the entire real number line, is both open and closed. Some people use a terrible word. They say it's clopen. Not a fan, but some people like to say that, so whatever. And then also, of course, the empty set is also both. So very, very generally, the empty set is always open and closed, and the set of your entire space is always open and closed. Are there questions about anything I've said so far? It's fine if there are. I'm happy to address questions. Because I definitely remember being moderately confused when I first learned about this stuff. I was like, what is going on with open and closed? If it were me, I would encourage you to keep these sorts of very basic examples in your head. This is an open set. This is a closed set. That's kind of the what I remember. Or in 2 dimensions. Actually, let's look at a couple of 2-dimensional examples. So let's say that we wanted to find, yeah, let's not do that one yet. So let's say we wanted to find the, yeah, let's say our function was f of xy equal to this, yeah, sure, this, let's do it that way. 6 over the square root of 4 minus x squared minus y squared. We'll find all the things, domain, range, open, closed. Or I should say, we'll talk about the domain and range and whether or not they're open or closed. So let's talk about the domain. So I need the stuff inside my root there, 4 minus x squared minus y squared, to not only be greater than or equal to 0, but to actually be strictly greater than 0, because we don't want to include the places that make it equal to 0. We don't division by 0. So then, as we usually do, if you see an x squared plus y squared, get it by itself. Okay, so my domain is the set containing all x and y such that x squared plus y squared is less than 4. Or if we want to use some words, it's the set of all points inside the circle of radius 2. Let's draw it. Do I want a dashed boundary or a solid boundary? I should really ask, am I including my boundary or not including my boundary? Who votes for including? Who votes for not including? Yeah, we're not including, right? Because I don't have an equals there in my inequality. So we're definitely not including, which should definitely give us a clue as to if it's closed or open if we are not including the boundary. So here's our boundary of our domain. I suppose I got a little ahead of myself. I should have said that we were going to check to see if it's the inside or the outside. So if it was the inside, 0, 0 should work. If I plug in 0, 0, oh yeah, that works. So we definitely want the inside. So first, is this bounded? It certainly is. Right? There are definitely strict limits as to how large x or y can be. So yes, it's definitely bounded. Is it closed or open? Well, I bet you all have some guesses. That's a yes. I see some guesses. Let's see some more guesses in the chat. How about in class? How about a thumbs up for closed, a thumbs down for open? I want to see some thumbs. I see some thumbs. I see a few thumbs. I see some thumbs. Or you can go to the middle if you're not sure. I said thumbs up for closed, thumbs down. Right. So if you want open, that's a thumbs down. Closed, thumbs up. Yeah, it's definitely open. And again, it's open. I really do like to think of openness as, well, one, it doesn't include the boundary, but two, I really like, I can pick any point in there and I can always draw a little circle around it that is still included in there. And no matter how close I get to the boundary, I can always do that. I just have to pick a circle that has a radius that's smaller than how far it is from the boundary, because there's always some distance between the point I'm picking and the boundary. Right? That's the whole idea, is you can't ever get to the boundary because it's not included. So hopefully I'm making it somewhat clear as to what's going on here. The range, let's talk about the range. All right, so I'm going to think about this. Oftentimes, not always, often it makes sense to start with what your domain is when you're thinking about the range. So for my domain here, well, I know that x squared plus y squared has to be less than 4. I also know that x squared plus y squared had better be greater than or equal to 0, just because it is. And then I'm going to, I really kind of want to talk about it two ways. First way, I'm thinking, okay, how big and how small can this thing get? Let's see. So if I want to make my whole function small, sorry, I think I wrote it small because I was talking about being small. So I want it to be small. I want to make the denominator large. What's the largest the denominator can be? Show me on your fingers. What's the biggest number the denominator can be? It is a number you can show me on your fingers. Oh, you're very close, but you've forgotten a small little thing. Yeah, that many, exactly. The biggest the denominator can be is 2. Right, square root of 4. Because if I want to make the denominator big, I have to make x and y as small as possible, or really x squared and y squared as small as possible. So I need to make those both 0. Then that's going to be 4, and 4 minus 0 is 4, and the square root of 4 is 2. And that's the biggest it can be. I can't make that denominator any larger. Because if x and y aren't 0, I'm going to be making these numbers bigger, and then subtracting them off is going to make the whole thing smaller. So the biggest the denominator can be is 4, which means the smallest the fraction can be is going to be, sorry, I said 4, I meant 2, is going to be 6 over the square root of 4, which is 3. That is the absolute smallest that can be, because that is the biggest the denominator can be. So then if I want to make it big, I have to make the denominator small. All right, how small can the denominator get? Well, I think I can get all the way very, very close to, I suppose it can't actually equal 0, but you can get closer and closer and closer to 0. So the denominator is getting closer and closer to 0. So we're getting something like 6 over 0, which is going to be like infinity. So it's probably the case that our range is 3 to infinity. We could be more algorithmic about it though if we wanted to. We could take this whole inequality that we have written here and manipulate it till we get to this. So I could, now this is going to be kind of gross. I feel like I should give myself a little more room here. If I wanted to do this, we could take our inequality and try to make it look like that. So first I'm going to negate everything. So 0, the negative of 0 is still 0, bigger than or equal to negative x squared minus y squared, bigger than negative 4. I took the negative everything, but had to change the direction. And then I'm going to add 4 to everything. So 4 plus 0 is 4. Then I have 4 minus x squared minus y squared. And 4 minus 4 is 0. And then I'm going to take the square root of everything. And then I'm going to take the reciprocal of everything. So the reciprocal of 4 is 1/2. And then I change the direction of the inequality again when I take the reciprocal. So I'm going to have less than or equal to 1 over the square root of 4 minus x squared minus y squared. And if something is bigger than 0, its reciprocal is smaller than infinity. Right? If I'm positive and I can be any positive number, then my reciprocal is also any positive number. And then I'm going to multiply everything by 6. 6 times 1/2 is 3. 6 times this is 6 over the square root of 4 minus x squared minus y squared. And 6 times infinity is still infinity. Oh yeah, we get everything from 3 to infinity. I don't love doing it this way, but some people really prefer kind of just thinking, okay, I can math it out the whole way. You can totally math it out the whole way, or you can think about how am I going to make this thing big? How am I going to make this thing small? Either way will work. It just depends on what works for you. And then again, this set is definitely unbounded and closed. We usually don't talk as much about the range being unbounded and bounded or closed versus closed, but it is worth mentioning. I suppose I should say it is closed and it is not open. This set here is open and it is definitely not closed. Personally, I don't think you need to specify that, but clearly that might not be the case. Okay, let's look at a couple more examples and then we'll start talking about some limits and some partial derivatives. So let's look at, yeah, I wanted to say, sure. Let's look at the following one. Let's look at f of x comma y equal to the square root of x minus y squared. All right, same deal. So at least in the beginning, the first steps to finding the domain should be just like they were back in 21A, meaning you're just looking for some sort of problem and trying to account for it. In this case, the problem is we're taking the square root of some stuff, and we know we can't take the square root of negative numbers. So we have to say, all right, our stuff has to be greater than or equal to 0. And then you can kind of do, I wouldn't solve for y, right? If I solve for y, I'm gonna have y squared greater than less than or equal to x. And then I don't really want to take a square root of things with an inequality. That just seems dangerous. I would really just leave this as x greater than or equal to y squared, because we can certainly graph x equal to y squared. And since my inequality has an equals in it, I know I want to include the graph that I'm going to graph. So x equal to y squared, that parabola opens to the right. I think, yeah, opens to the right. So here's x equal to y squared. And certainly that whole boundary is part of my domain. And then just like any other time I'm trying to find where it is, I'm going to pick a point that I know is not on the boundary. So let's pick the point, like, I don't know, let's pick the point 6, 0 and see if it's in my domain or not. So x is 6, y is 0. Yep, that checks out. So everything on this side of the boundary, including the boundary, that's my domain. Wanted to write it as a set, which as you might hear by my tone, I never want to write it this way. I feel like it's just like, yeah, I'm just saying the same thing I already said. The domain is the set including all points x and y such that x is greater than or equal to y squared. If I were trying to describe this using words, I would say it's everything to the right of the parabola x equals y squared, including the parabola x equals y squared. All right, now for the fun questions. Bounded or unbounded? Is there a limit to how big x or y can be? There is, right? So really, I should say to be unbounded, there has to be a limit on how big x and how big y can be, right? So you could have something where x was bounded and y wasn't. For example, well, I'll give you an example, but like both x and y have to be limited to be bounded. So this is definitely unbounded. And I'm going to ask you a negative question here. Is it not open or is it not closed? Let's see. So let me show you. So let's see. So here's a point that's in the domain. Right there on the boundary. Can I make a little circle around it that's still included completely in the domain? So let me ask you, is this circle, is every point in that circle also in the domain? No. So it's not open. Because to be open, we have to be able to pick any point. You have to be able to draw a little tiny circle around it and have that still be included in your domain. And it's not. So definitely not open. Now I should point out, as has been mentioned a few times, not open doesn't necessarily mean it's closed. It could also be not closed. Yes, definitely. So I'm gonna say it in a slightly different way. So to be open, any point in the domain, I'm gonna write this down again. So to be open, for any point in the domain, a small circle around that point must also be completely contained in the domain. The circle can be as small as you want it to be. It does have to have a positive radius, though. It can't have a radius of 0. So for that point right there, no matter how small I make my circle, you're going to have parts of it that are not included in the domain, which makes it not open. Whereas in this previous example, any point that I picked, even if it was super duper close to the edge there, since it's not touching the edge, I can take the distance from it to the edge, cut that in half, and make a circle of radius, whatever that is, around it, and it's still going to be included in the circle that's right there. So I can find a little, that little circle right there is still included in there. And no matter how close I get, as long as I'm not on the boundary, I can always find a circle that is small enough to be included in the domain. Does that help? So again, this point, or I should say, this domain is not open because that point there, any circle around it, no matter how small I draw it, is going to include stuff that's outside of the domain over here. Is it closed? Closed is always hard for me. So if I'm asked about closed, I'm going to ask myself, okay, is the complement open? So I look at all this stuff over here that doesn't include this boundary. Is this entire set over here open? Well, I think it is, because any point I pick in there, a small circle around it is also going to be included in there. So I think it is closed. In fact, I shouldn't say I think it is. I know it's closed. Typically, if a domain includes its boundary, it's closed. So this definitely is closed. Something else I want to say there, I feel like. No, I guess that's it. Range. Let's talk about the range. So this one, I feel like, doesn't lend itself as well to doing something mathy. I feel like we just kind of have to talk about it. So definitely we have a lower limit to how big this can be, or a lower limit to how small it can be. Right? Square roots only ever give you non-negative results. So definitely the smallest this could be is 0 at the very smallest. Can it be 0? Yes, we definitely get to 0 by letting, take your pick. X could be 4 and Y could be 2. Or X could be 0, and Y could be 0, right? There's a lot of different ways to get to 0. You just have to think about, can we get 0? Sure. So certainly my function can go as low as 0. And then can it get really big? It sure can. If I let Y be 0 and make X as big as I want it to be, the output can also be as big as I want it to be. If I want the output to be 1 billion, I'm going to let X be 1 billion squared and Y be 0, and then make it 1 billion. So my range is certainly everything from 0 inclusive to infinity. My range is also unbounded. My range is also closed and not open. So I think it is easier to kind of justify here, oh yeah, this is definitely closed because we include all the boundary points. There's only one, it's 0, we included it. And it's definitely unbounded, because the function values can get as large as you want. I'm sorry. Sure. Let's look at one more. We'll do one more. Let's say we have f of xy equal to natural log of x squared plus y squared minus 4. Interesting. All right. So in this case, we need x squared plus y squared minus domain. We need x squared plus y squared minus 4 to be greater than 0, which is going to lead to x squared plus y squared greater than 4. So when I'm looking at this already, I'm thinking, okay, it's probably not going to be closed because we're not going to include our boundary, which means it's probably going to be closed. Let's see. So if I draw this out, I again got a circle of radius 2. And if x squared plus y squared has to be greater than 4, 0, 0 isn't going to be part of the domain. I don't want everything inside the circle. I actually want everything outside the circle. Which I'm never good at drawing this. Like, okay, here it's everything, right? Yeah, okay, fine. Yeah, okay. Not my best. But we don't want anything there, right? That's off limits. So definitely not bounded. X and Y can be about as big as you want them to be. And it is certainly not closed. I don't include my boundary. Or you could say that the complement is closed. right? If the complement, right? Well, that doesn't say, I guess that doesn't show it's not closed. Okay, fine. It's just not closed. And then it is open. You can say it is open because the complement is closed. Or because you can pick any point in there and a small circle around it is still included in it. Again, really, most of the time when it comes to open and closed, open sets don't include their boundaries. Closed sets do include their boundaries. That's kind of it. How about the range? Well, okay, so here's what I'm thinking about for range. I know that the logarithmic function, y equal to the natural log of x, has a range of everything. Negative infinity to infinity. As long as x gets to go from 0 to infinity. So as long as my insides here get to go from 0 to infinity, the function should go from negative infinity to infinity. And it does, right? My insides are definitely can get as close to 0 as you want. I can make x equal to 2.000000001 and y equal to 0. And the insides are going to be super close to 0, which means my values are going to be super negative. And then I can also make these super big, which makes the natural log eventually super big. Although natural log takes a long time, but yes. So my range here really is everything. And just to be specific, my range is unbounded. My range is open. My range is closed. Okay, one more really stupid example. Sorry, this one wasn't, not to say this one was stupid. One more example that happens to be really dumb. But I feel like I should mention. Let's say my function was f of xy equal to the set containing, oh, wow, okay, let's back up there, James. Okay, getting ahead of myself. Sorry, f of xy is equal to the function, the square root of, sure, negative x squared minus y squared minus 9. This is not going to be a very exciting function. Domain. So negative x squared minus y squared minus 9 has to be greater than or equal to 0. Okay, so I bring the x squared plus y squared over to the other side. I have negative 9 bigger than or equal to x squared plus y squared. And that's not going to work out. There are literally no values of x and y. There's no domain. So what is my domain as a set? It's the empty set. I don't think anyone would ever ask you this, but I'm not that imaginative, so maybe someone would. So domain here is empty, and that means it's open or closed. You're all supposed to say it's. So this set is both open and closed. Is it bounded? Why is there no domain? Good question. So if I look at, so for this function here, I need my insides to be greater than or equal to 0. But if my insides are going to be greater than or equal to 0, there's literally no way that's going to happen. Because if I'm trying to solve this inequality, I'm going to get x squared plus y squared less than or equal to 9. But we know that no matter what x and y are, x squared plus y squared is always greater than or equal to 0. And there's no possible way for a thing to be both bigger than 0 and less than negative 9 at the same time. I can't find any x and y values, right? X could be 1 and 2. And 1 squared plus 2 squared is 1 plus 4, which is 5. It doesn't work. No matter what you pick for x and y, x squared is going to be positive, y squared is going to be positive, and it won't be less than or equal to negative 9. So that's why there's no domain. The point of this question really was to get a domain that was the empty set, which we did, which again feels weird because if your domain is the empty set, you don't really have a function, right? There's nothing you get to put into it to get anything out of it. And then, is it bounded or unbounded? Well, it's clearly, I take back the word clearly automatically. I don't think anything's clear about this example, but I'm pretty confident it's not unbounded, right? X can't be anything, Y can't, literally X and Y can't be anything. So it's not unbounded. I think you could say it's bounded. I think that's okay. Because X and Y don't have very, very, very strict limitations. Like you can't be anything. So again, I don't think someone would really ask you that, but it seems worth pointing out.
So like, I would have thought that it was unbounded as like, it's like X and Y have to be greater than 0, right?
Well, no, so no, actually, we need this condition, and we know that this happens to be true, that X plus Y squared is required to be greater than 0.
Yeah. Oh, okay. So like, it's just. So how is it bounded? Like we just.
So let me draw the domain for you. The domain is the part I shaded in, which there isn't any, right?
Yeah.
So basically, when I'm thinking about bounded versus unbounded, if I'm drawing the domain, a bounded domain has a clear limitation, right? There's a boundary on any side of it.
Yeah.
Where, so like, for example, we've seen some examples where like the domain was everything inside a circle. Right? This domain, definitely bounded, right? X, Y, I'm stuck, right? I'm contained on every side. Whereas this other one we did where it was like X greater than Y squared or whatever, this one here, right? I can keep going in this direction and that direction for as long as I want, right? There is no containment of X and Y in at least some direction. So that's kind of the difference.
So it's like, it's bounded by nothing.
Right, there isn't anything to even be contained.
So could you say it's bounded by 0, 0? Or is that like,
I wouldn't say that. We don't typically talk about bounded by what you're bounded by. We're just bounded or unbounded. But that's a fair question. Yeah. Again, I wouldn't sweat that example too much. It's kind of funky, but yeah. All right, let us move on to talking about some limits. So limits of multivariable functions. And so before we get there, let's just remind ourselves of a few things from 21A. So if you're doing limits in 21A, there's kind of, I would say there's maybe 3 rules to remember. So you're doing like the limit as x approaches 2 of x squared plus 3x. The first rule is just if you can plug in what x is approaching and get a real number out, good to go. So if I plug in 2 and I get 4 plus 6, which is 10, check, that's the limit. So first thing you want to try is plug it in. If you get an answer out, probably good to go. The second thing, which is probably most of what we're going to encounter, is if you have a limit of the following type, where you have, say, like x squared minus 4 over, I don't know, 3x minus 6. If you plug it in here, you get 0 over 0. So when you have a 0 over 0 indeterminate type, typically we have to do something. Typically, we often do algebra. More generally, some sort of manipulation. I should say algebra. There's also the sine x over x situation, right? Where that limit as x goes to 0 is 1. So be aware of those things. We're going to manipulate this. We're going to get the limit as x approaches 2 of x minus 2 times x plus 2 over 3 times x minus 2. The x minus 2's cancel. And then you have the limit as x approaches 2 of x plus 2 over 3, which is just going to be 4/3. So that's kind of the second thing to remember. If you got a 0 over 0 type, it's going to require some sort of manipulation or maybe something else that's going to be kind of new for multivariable functions. And then thirdly, if your function is piecewise, different from different directions, say it's x squared plus 1 when x is less than 2, and x plus 1 when x is greater than or equal to 2, we have to look at the limit from each direction. So if I look at the limit as x approaches 2 from the right of f of x, I'm going to use the piece where x is bigger than 2. And that's the limit as x approaches 2 from the right of x plus 1, which is equal to 2 plus 1, which is 3. Versus the limit as x approaches 2 from the left. That's going to be the limit as x approaches 2 from the left of x squared plus 1. If I plug in 2, I'm going to get 2 squared plus 1, which is 5. And since the left and the right hand limit don't equal the same thing, the limit doesn't exist, right? What we kind of have a situation here is something like where, right, the left hand side is doing this. And the right hand side is doing something like, you know, this. Limit does not exist. The left and right hand side aren't getting close to the same value. So limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. Then the limit doesn't exist. Okay, so those are kind of the things to remember when it comes to limits. If you can plug it in, get a result, good. If you get a 0 over 0, you need to do some sort of work. And then if you have limits from different directions approaching different values, that means the limit doesn't exist. Let's look at some multivariable examples, like the limit as x comma y approaches 2 comma 3 of x squared plus y squared minus 1. Well, can I just plug it in? Let's see. If I plug in 2 for x and 3 for y, I get 2 squared plus 3 squared minus 1. That's 4 plus 9 minus 1. That's going to be 12. I don't see any reason why that shouldn't work. There's no weird undefinedness around the point 2 comma 3 or really anywhere. Okay, on the other hand, and I will say not always, but a lot of the examples, well, no, actually, take it back. Let's look at the limit as x, y approaches 3, 3 of x squared minus y squared over x minus y. Well, here we have a 0 over 0 type. And so when we have a 0 over 0, what's going to be true a lot of the time here is when we have a 0 over 0, either you're going to be able to do some algebraic manipulation, or you're not, which we'll see in just a second. Here, we can do some factoring. I can rewrite this as the limit as x, y approaches 3, 3 of x minus y times x plus y over x minus y. The x minus y's cancel, and then we're left with the limit as x, y approaches 3, 3 of x plus y, which is 3 plus 3, which is 6. So if you can do some algebraic manipulation, great. But sometimes you can't. Like this limit as x, y approaches 0, 0 of 4xy over x squared plus y squared. This is also a 0 over 0 type, but we can't do any algebra. There's nothing we can do about this. So here's what we're going to do instead. Typically, what we're going to do is we're going to usually assume the limit doesn't exist and then try to show it. So just like, or similar to like before, where the limit from the right and limit from the left didn't equal each other, and that meant the limit doesn't exist. If you have the limit approaching the point 0, 0 from any different directions being different, the limit's not going to exist. The thing is, in 2 dimensions, we have a lot more directions. you can come at the point 0, 0 from literally any one of an infinite number of directions. So for example, yeah, I'm through. So here's my XY plane. Here's the point 0, 0. I'm going to approach it along this line. Along the line y equals 0. That's totally valid, right? I'm approaching the point 0, 0 and from a specific direction. So when I look at the limit as x, y approaches 0, 0 of 4xy over x squared plus y squared, I'm literally going to substitute in y equals 0. This is going to be equal to the limit. Well, if y equals 0, I don't have to write that part anymore. The limit is x approaches 0 of 4 times x times 0 over x squared plus 0 squared. Okay, here's where you have to be extra careful. What's 4 times x times 0? Okay. What's x squared plus 0 squared? What's 0 divided by x squared? There is a very, very correct and clear answer here. 0 divided by x squared is, yeah, it is 0. Now, some people might be thinking, well, James, aren't you dividing 0 by 0? And the answer is no, I'm not. Because x is approaching 0, but is specifically approaching and not equal to 0. And when taking a limit, you're saying we're getting really, 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 really close to the 0, but we're actually not getting there. We're just getting closer and closer, but not equal to 0. So this 0 divided by x squared is very specifically 0 divided by anything but 0, really. And 0 divided by anything but 0 is 0. 0 divided by 5 is 0. 0 divided by 1 is 0. 0 divided by 0.0000001 is still 0. So this division here says, okay, I've got the limit as x goes to 0 of 0. And the limit of a constant is just a constant. So this limit approaching from that direction is 0. But then let's look at another direction. Let's say I come from the direction of y equals x. So now if I do that, the limit as xy approaches 0, 0 of 4xy over x squared plus y squared. You can make either choice. I'm going to choose to replace y with x. I'm going to have the limit as x approaches 0. Fine. As x approaches 0, looks terrible. Of 4 times x over x squared plus x squared. But 4 times x is 4x squared. And x squared plus x squared is 2x squared. And x squared divided by x squared cancels out. So I have the limit as x approaches 0 of 2, which is 2. And now look, we have limits from different directions having different values. That means the limit doesn't exist. So here we can say that this limit as xy approaches 0, 0 of 4xy over x squared plus y squared does not exist. You don't have to write because, but I'm going to write because limits from different directions have different values. So it's very much like this situation here, where the left side is doing something like this and the right side is doing something like that, and they're not getting close to the same value. It just looks way, way funkier in 3 dimensions. In fact, I do think in this section, it is worth exploring or visualizing what things look like. So if we want to look at what this looks like for just a moment, and I know, let me reshare my screen here, sorry. Share screen 2. So, yeah, I don't care about you. Go away. So we want, yeah, okay, no, I don't want my unsafe changes. Okay, sorry. So if we graph this thing, 4xy divided by x squared plus y squared. Look at this thing. it looks like you've got some pretty serious discontinuity at the origin there, right? Up here, it's like super high, and down here, it's like way down. Like it looks like there's no way the limit at the origin could exist, because if you come in from right, so look, I was kind of super cool, and I'm getting a little excited here. If you come at it from the y equals x direction, look, the limit's 2. In fact, it's a constant value of 2. Whereas if you come at it from the like y equals 0 direction, I know it's kind of hard to see, but right, like along the either x equals 0 or y equals 0, you're getting a value of 0 the whole time. So from these two directions, you've got vastly different values, right? One's way up here, one's way down here. They can't be getting close to the same thing, so the limit can't exist. It's kind of neat. It's a pretty graph, I think. I don't know. Yeah, it's cool. Okay, anyway. I can't express like how jealous I am that you all get to take 21C and have like cool 3D graphing utilities available to look at. Like, I know it doesn't seem like that big a deal, but I did not have such things. I had to look at the pictures in the book and they were pretty good, but like I couldn't do any function I wanted. So use it. It's a great tool and you are fortunate to have access to it. All right, let's look at some more examples. Okay, we got time. So let's say we wanted to look at this limit. The limit as x, y approaches 0, 0 of 8x squared y over x to the 4th plus 3y squared. And we can see, of course, if we plug in 0, 0, we're going to get 0 over 0, indeterminate form. So for these ones, here's what you should usually do. If you get a 0 over 0, you want to keep trying things. You're going to try any path that seems reasonable that goes to the origin. And if you keep getting the same value, keep trying. I would say try at least 3 or 4 things before you're like, well, so I should say, if you keep trying things and you get the same results back and back again and again and again, you might start to think, well, maybe the limit exists. Maybe it's equal to this value I keep getting. If you think it exists, then you have to do other work to try and show it exists. But most of the time for things like this, you're going to get non-existence. So let's look at this one. I always recommend you should always try y equal to 0 or x equal to 0. I feel like people overlook this one, but it always will give you something. Often it will give you 0. So if I try, let's try x equal to 0. Then I'm going to get the limit as y approaches 0 of 8 times 0 squared times y over 0 to the 4th plus 3y squared. And that's going to be the limit as y approaches 0 of 0 over 3y squared, which we know is going to end up being 0. Because 0 divided by anything that's not 0 is 0, and the limit of a constant is 0. Most of the time, going along y equals 0 or x equals 0 is going to give you 0. Not always, though. It doesn't always have to. Okay, so now we need to pick another path that will hopefully get us a different value. Question. Oh, wait, so she had a question first. Go ahead. No, so this one. So I said you could. So I said you could pick x equal to 0 or y equal to 0, and I decided to pick x equal to 0. So for each x, I plugged in 0. Right, so I have 8 times 0 squared times y over 0 to the 4th plus 3y squared. So, okay, sure. So if okay, so graphically, I'm on the line x equals 0, right? So I'm on the y-axis here, and I'm approaching the origin, right? Because that's what we started with. X, y goes to 0, 0. So I'm approaching the origin on this line. X is already 0, right? I can't move off. I can't move off the line. X is 0. I'm stuck. I've decided. So I'm not going to write the x part of my limit anymore because I've chosen x to be 0. But then as I'm moving either down this way or up this way, y is approaching 0. So that's why I'm still writing the limit as y goes to 0. Basically, whichever thing you set equal to something, that one kind of disappears and the other one still has to be in the limit. Do you have a question?
No,
Okay. So yeah. So let's try another path. My usual next go-to choice is y equal to x. That's a very common choice. Or really, you can pick y equal to any multiple of x. So if you wanted to, you can pick like y equal to 3x. Let's do something. Let's do that just to be a little different. Let's say we pick y equal to 2x, just to change it up a little bit. Notably, the thing you pick has to go through the origin. And it does, right? X is 0, y is 0. Or whatever point you happen to be approaching, right? Usually it's the origin because like that's what we don't deal with. So if we do this, we're going to get the limit as I'm going to replace y with 2x. So I'm still going to have x going to 0. And then I'm going to have 8 times x squared times 2x over x to the 4th plus 3 times 2x squared. All right, let's see what happens. So I've got the limit as x goes to 0 of, let's see, 8 times x squared times 2x is 16x cubed. And x to the 4th plus 6 times 2x quantity squared is going to be x to the 4th plus 4x squared times 3 is 12x squared. So I have a 0 over 0. So when you have a 0 over 0 like this, what you want to do is factor out as much x as you can from the denominator. So if I have x to the 4th plus 12x squared in the denominator, I can factor out an x squared. If I do that, I still have 16x cubed on top, and I have x squared times x squared plus 12 on the bottom. And then the, so that's a good question. How did I choose y equals 2x? I picked a path, and I guess I could have drawn it as well. Basically, I'm just picking a plausible choice. We're going to find out that this actually doesn't work for this. Well, it's not that it doesn't work, it doesn't give us anything different. But really, normally I would have picked just y equal to x. I just decided to make it a little bit different. But really, yeah, so I usually go either y equals x, or sorry, y equals 0 or x equals 0 first. And then I usually try y equals x or a multiple of x next. Something that has to go through the origin. X cubed over x squared is x. So we're left with the limit as x goes to 0 of 16 times x over x squared plus 12. And now when I plug in 0 for x, I get 0 over 12, which is 0. Which is fine, except it doesn't tell me that this limit doesn't exist yet. Because so far both limits are 0. And if they're the same, that doesn't mean, right, we're not done. It doesn't mean the limit exists, right? There's literally an infinite number of other choices you can make that might show it doesn't exist. But we don't have evidence yet to show that it doesn't exist. So then I start thinking about, well, what about like y equals x squared? I kind of usually just start going up with higher powers. Now, when I do this, I try to think about if I plugged in x squared for y, I'm really often trying to make a choice so that when I simplify my expression, the highest power on top and the highest power on the bottom are the same. So if I pick y equal to x squared, what's my power on top going to be? X to the what? Ooh. And if I put y equal to x squared on the bottom, I'm going to get x to the 4th plus 3x to the 4th. So that's a good indicator that it's probably going to work because the degrees on top and the bottom are all going to be the same. So if we do that, we're going to get the limit as x goes to 0 of 8x squared times x squared over x to the 4th plus 3 times x squared squared. Simplifying, we get the limit as x goes to 0 of 8x to the 4th over x to the 4th plus 3x to the 4th is 4x to the 4th. And that's going to be the limit as x approaches 0 of 2, which is 2. So we got a different value. Great. That means this limit does not exist because limits from different directions that go through the origin have different values. So when you are doing these problems, specifically for limits as x, y approaches 0, 0 of some function of x and y, if we have a 0 over 0 type, here are the paths I recommend trying in the order I usually try them. So it's often worth trying y equal to 0 or x equal to 0. You might even do both. So Most of the time they'll give you the same result, but sometimes they won't. Sometimes they'll literally give you different things and then you're done. And then I would usually try y equal to x or y equal to some multiple of x. Or if you really like, x equal to some multiple of y. And then powers. Like y equal to x squared or x equal to y squared. Or y equal to the multiple of x squared or x equal to a multiple of y squared. And the list goes on, right? You can have higher, so then you can just keep going kind of, right? You can have y equal to x to any power or x equal to y to any power. I should say those positives should be power. Those powers should be positive. Let's do a negative power, 0 to a negative power is undefined. There are other functions that work as well, but these are kind of the usual list of things we start trying. I bet you could think of other functions that go through the origin, but these are kind of the standard list of where we start with. Now I'm trying to think like what else would work. I mean, you can just like you could pick something great. Like here's an example of something I probably wouldn't pick, but would totally work. Y equal to e to the x minus 1. That technically goes to the origin. Plugging it into these functions to try and get a limit working probably wouldn't help. So this would not, I should say probably not, a good choice. But it would be a valid choice. Can you explain why we try these things again? So we can see two, yeah, right, exactly. The reason we're trying these different paths is because once we get two different values for the limit, we're done. We can say this limit does not exist. So then you might be wondering, well, do we ever get these limits to exist? And yeah, they do exist sometimes. So let's look at this next example. And I'm going to do it two ways that are not here. So let's say the limit as xy approaches 0, 0 of 3y squared x over x squared plus y squared. And I will point out that this is a 0 over 0 type. So I will tell you, if you pick a bunch of different paths, you're going to get 0 every time. If you pick y equal to 0, you're going to get 0. If you pick x equal to 0, you're going to get 0. If you pick y equal to x, you're going to get 0. You can check that on your own. This limit is 0, so it makes sense that any path I pick ends up being 0. But how do we show it 0? Well, there are 3 ways I can think of. I'm going to show you 2 of them. I'm going to save the third one for not doing it if we don't have to do it, to be perfectly honest. But we'll definitely do the delta epsilon limit if we have to next time. I hope we don't have to though, because it's always a pain. So here's one way. Use the squeeze theorem. So there's a thing about x squared plus y squared. It's always greater than or equal to 0. And what we can do here is we can say, well, it's true that y squared is definitely less than or equal to x squared plus y squared. For sure, 100% of the time, no ifs, ands, or buts about it. It's also true that y squared is bigger than or equal to 0. So this method I'm using right here wouldn't work if we had like 3yx on top, because you couldn't say that y is bigger than or equal to 0. And then we're going to manipulate the middle to look like what we're trying to keep limited, just like you would with the regular squeeze theorem, right? Like if we were doing something from back in the day where I was trying to find, like the limit as x goes to infinity of cosine of x, let's say cosine squared x plus 2 over 3x plus 1, we would do the same sort of thing. We're like, okay, cosine of x is between -1 and 1, and then we'd square both sides, and then we'd add 2x, and right, it's the same kind of thing where we're going to take this inequality that we're starting with and try and make it look like what we've got. So I'm going to multiply everything by 3x. Great, 3x times 0 is less than or equal to 3x times y squared is less than or equal to 3x times x squared plus y squared. I suppose I should point out that if x were negative, we'd have to flip the direction of the inequalities, but we're not going to worry too much about that because it's not going to matter. And then, well, that's obviously 0. And now I'm going to divide everything by x squared plus y squared. So 0 divided by x squared plus y squared is less than or equal to 3x times y squared divided by x squared plus y squared. is less than or equal to 3x times x squared plus y squared divided by x squared plus y squared, which I'm not going to write down. So check out what we've got. We have that the thing we want to take the limit of is between 0 and 3x. Great. Let's take the limit of the ends of the outer parts. The limit as x, y goes to 0, 0 of 0 is certainly 0. And the limit as x, y goes to 0, 0 of 3x. Sorry, that was terrible. I'm gonna have to write that again because it's too terrible. Limit as x, y goes to 0, 0 of 3x is also 0. So the limit of that's 0, the limit of that's 0. Squeeze theorem says the limit of the inside part has to also be 0. That's definitely one way of doing this problem. There is another way that will sometimes work. Specifically, it usually works if you have like an x squared plus y squared. So let me show you the other way of approaching this one. And there's definitely a homework problem. Well, no, sorry, I was thinking for not having any of these class, there is a homework problem that asks you to do this next part. So instead of doing what we just did for the limit as x, y goes to 0, 0 of 3y squared x over x squared plus y squared. What we're going to do is we're going to convert to polar coordinates, which your teacher is going to assume you learned in 21B, even if you didn't. So here's what we need to know for this. Draw a little thing, a little segment, angle theta, distance is r. And then drop a perpendicular. This is going to be x. This is going to be y. So we have a couple of equations. X squared plus y squared equals r squared. And x equals r cosine theta. Y equals r sine theta. Those are the important things to know about how to go between polar and rectangular coordinates. So notably, if x, y is going to 0, 0. It doesn't matter what your angle is. All that matters is that your radius is also going to 0. Right? Your angle could be pi over 4, or pi over 2, or 2 pi over 3, or 3 pi over 2. Right? Whatever way you're pointing, as long as your radius is getting smaller and smaller and smaller and smaller and smaller, you're getting closer and closer to the origin. So x, y going to 0, 0 means that the radius is going to 0. And we don't care about the angle. Theta can be anything. This is also used to show other things don't exist, because sometimes you'll be left with theta that can be anything. And they're like, oh, we get anything. So here, I know it's I'll wrap this up real quick. So I'm going to rewrite this as the limit as x, well, not x anymore, as r goes to 0 of 3 times y is r sine theta. So r squared times sine squared theta. And x is r cosine theta, so r cosine theta, over x squared plus y squared, which is r squared. All right, do the division. Those cancel. We're left with the limit as r goes to 0 of 3 times sine squared theta times r times cosine theta. And I don't care what theta is, theta can be any angle, but sine of theta is something, cosine theta is something, and you multiply that by r, and r is going to 0. This is going to go to 0. There's no other option. Now, I will point out, if that r hadn't been there, right, if that r had canceled, then we'd have a problem. Then this limit wouldn't exist, because this limit would be 3 sine squared theta cosine theta, which can end up being really kind of any value, because theta can be anything, not any value, but like you get lots of different values, which would mean the limit wouldn't exist. So I'll just say, if we had done this and r hadn't been there, the limit would have not existed, because you get multiple values, because theta can be anything. And I would show you an example of that, but we're out of time. So we'll do that one next time.